Let's do another example of calculating ds by geometrical intuition, this time for a sphere. So imagine that I ask you, calculate the surface area of a sphere of radius r. That's the only thing I tell you, okay? So how do you do it? First of all, you would say, okay, use spherical coordinates, yeah? And I'm not even going to write the equation for r, because in spherical coordinates it's involved cosine times sine and blah blah. It's quite a long thing, yeah? But what you do remember is that you had three variables. You had r, you had theta, and you had phi, which corresponds to the distance to the origin and the two angles theta and phi, which they have not appeared yet. There is a bit of lag. There they are. Okay. So those are the three variables in spherical coordinates. If you want to integrate the surface of a sphere, we just fix r equals capital R. So that now we have fixed the radius, so we are on the surface of a sphere. So then our two variables are theta and phi. Okay, so those are going to be our two parameters that define the parametric surface of a sphere. And what are the limits? So phi goes between 0 and 2 pi, while theta goes between 0 and pi, as you already know by now, because the polar angle stops at pi. So now we are ready to calculate the surface area of a sphere by doing the surface integral of ds. Okay, but we need to figure out what ds is. And that's when we are going to use geometrical intuition. So figure out ds. So the trick is the same as earlier. We start by fixing the two parameters. So theta equals theta 0 and phi equals phi 0. Okay, and therefore we are at some point along the surface. Let's say that we are here. Okay, now we increase the two parameters by a differential amount. So phi goes to phi 0 plus d phi, and theta goes to theta 0 plus d theta. Okay, so here I am drawing, and this drawing becomes a bit ugly. I agree with you. It's not easy to find ds for a sphere with geometrical intuition, but I'm showing you that it can be done. Okay, so we increase theta by an amount phi by an amount d phi. So this means that if phi was 0, for example, we are along the x-axis. Now we move by an amount d phi around the z-axis. So we increase d phi and we end up here. Okay. And at the same time, we increase theta by an amount d theta. Okay, so remember, theta is the angle between the point and the z-axis. So it's this angle here. So if we increase theta by an amount d theta, we are moving down here. Okay, so by doing the two things at the same time, we end up here, and this creates this ds area here. Okay, so the rectangle created, and I call it rectangle between quotation marks, is ds. So we need to find the area of this rectangle. So in order to find the area of this rectangle, you need to find the arc lengths, this arc length and this arc length, and multiply them together. This arc length is very easy. Since this angle is d theta, and the distance from the origin to the surface is r, then the arc length is just r times d theta. Okay, so ds is equal to r d theta. So that's the first arc length, and now we need to multiply times the second arc length, which is this arc length. Now this is not so easy because the angle is d phi, but now the distance in which this angle is defined, so this distance here, yeah. So that's not r, because it's the distance from the sphere to the z-axis, because the angle phi is defined with respect to the z-axis. Okay, and therefore this distance here, you need to figure it out by trigonometry. And the way to figure it out is, I have a drawing here of this triangle, but maybe it's best if I do a cross section. So this is z, and let's say this is x, and we have our sphere here. Yeah. and we need to figure out this distance here. So this is the distance we need. We know that this distance is r, and we know that this angle is theta, and we know that this is a right angle triangle. Therefore, we know that this distance here must be equal to r sine theta. That is the distance there, which is this distance here, and therefore this arc length is that distance times the angle. So r sine theta times d phi. Okay, so when we multiply those two arc lengths, we end up with ds equals r squared sine theta d phi. And that is the correct ds for the surface of a sphere. Okay, later I will show you other methods of finding ds, because I think that this is not very practical, to be honest, but I think it's nice to show you that it can be done. So let's do now the calculation. So the surface of a sphere is just the integral of this ds, which is r squared sine theta d phi. So what are the limits? Theta goes between 0 and pi, and phi goes between 0 and 2 pi. We can bring r squared outside because it's a constant. We can do separation of integrals, 0 to 2 pi of d phi, and then 0 to pi of sine theta d theta. So this is equal to r squared times 2 pi times, this will be minus cosine phi defined between 0 and pi. Okay, so this will be equal to minus minus 1, which is 1, minus 1, so it's 2. Okay, so the final answer is 2 times 2, 4 pi r squared, which is equal to the surface area of a sphere. Okay, similar to what happened with the cylinder, we can also do an alternative interpretation in which we calculate a tiny ribbon around this sphere, okay, and find the ds for this ribbon, okay, and this we call it ds prime. And this ribbon has a width equal to r times d theta, because we're increasing theta by a certain amount. Let's imagine that this ribbon, so if we draw z and x, and this is the sphere like this, let me draw it again. This is the sphere like this, yeah, this is a cut plane showing 1/4 of the sphere. So the ribbon, maybe let's say, goes from here to here. Okay, so the length of that ribbon, if we have increased our angle theta by an amount d theta, and this length here is the radius r, so obviously this arc length is r times d theta. Okay, which is what I wrote here, r times d theta. And now what is the circumference or the width of this tiny strip? If we cut it and we expand it, this becomes a rectangular strip like this, whose height is r times d theta, and whose length is the circumference of this circle. Okay, and once again the circumference of this circle is 2 pi times the radius, and the radius of this circle is r sine theta, as we calculated here. We calculated there, yeah. So the length of this circle is 2 pi times r sine theta, and this will be equal to our ds prime. So now the area can be written as the single integral of ds prime, which is the single integral of 2 pi r squared sine theta d theta between theta equals 0 to pi, whose answer is the same. So 2 pi r squared is a constant, and then the integral from 0 to pi of sine theta d theta is equal to 2, so we get 4 pi r squared, which is the same answer. Okay, and by the way, you see how easily it was. So it was 5 lines, and because we did the steps very slowly, in 5 lines we have calculated the surface area of a sphere. Okay, this was the problem with Archimedes was most proud to have solved. Who knows how many weeks, months, or years he took to trying to find out the exact mathematical equation for the surface area of a sphere and how proud he must have felt. And here we have calculated it in 5 lines or even in 3 lines here. Okay, so that is the power of surface integrals. Good. See you in the next video.